Have you ever seen an interesting flower and thought, I wonder what kind of flower that is? Wouldn't it be great if you could pull out your phone, take a photo of the flower, and have an app tell you, that's a daisy or that's a lily? Well, that sounds like something a CNN could do. Classify the type of flower in an input image. Pre-trained networks can classify an image into hundreds of predetermined categories, from vacuum cleaners to volcanoes, elephants, and cauliflower, but not all the flower species you'd need for your flower app. So you can't just use a pre-trained network in your app. But rather than start over from scratch, why not take a network and modify it to fit your problem, and train it on some images of flowers? This process of taking a pre-trained network, modifying it, and retraining it on new data is called transfer learning. And it's a very effective way of tackling many deep learning problems. To perform transfer learning, you'll need three things. First, you'll need a network to train. The point of transfer learning is that you'll get that network by starting with a pre-trained network and then modifying it. Second, you'll need data to train with. This means you need example images for which you already have the correct label. In machine learning terminology, this is known as supervised learning. The network will learn from examples with a known correct answer. Last, you'll need to specify a set of training options. Training involves applying an algorithm that iteratively improves the network's ability to correctly identify the training images. This algorithm can be fine-tuned with many parameters, such as how many training images to use at each step, the maximum number of iterations to take, the learning rate, or how aggressively new iterations should change the network parameters, and so on. So Matlab needs you to specify a set of these training options when you train a network. But don't worry, you can often just use the default values for most parameters. Once you have these three components, the network, the training data, and the options for the training algorithm, training is pretty easy. Pass the three pieces to the train network function and wait for the train network to be returned as output. In the next activities, you'll create the three components needed to perform transfer learning for the flower images. During training, the network weights are adjusted so that the network learns to associate the given inputs with the given outputs. But even if the network can correctly classify all the training data, did it really learn anything? The real use of a network is to apply it to new images it hasn't seen before. It's good practice to reserve some of your training data for testing. This reserved test set is not used to train the network, only to evaluate its performance. In this interaction, you'll use the split each label function to divide the images in the flowers folder into two separate data stores, one for training and one for testing.
When training a network, your training images may not be sufficiently varied. For example, these images of flowers are generally taken up close with good lighting. But if you're trying to build a mobile phone app, you really want the classifier to be able to cope with imperfect images, odd angles, substandard lighting, not well framed or cropped, and so on. An efficient way to handle these situations is to use an augmented image data store. The augmented image data store function takes an output image size and an image data store as inputs. The augmented image data store that's returned can be used as the training data input to the train network function. The images will be resized, but you can use optional inputs to control the preprocessing behavior. You can use the image data augmenter function to set up a set of transformations that you can apply to your images to make an augmented training set. These transformations include rotations, reflections, translations, shears, and scaling. You then pass the image data augmenter variable to the augmented image data store function as an optional input. Again, the augmented image data store can be used as the training data input to the train network function. Your training images are pre-processed automatically during the training.
When you look at the layers of a pre-trained network, you'll see that most of the layers are convolution, pooling, and rectified linear unit layers. These take the original input image and extract various features that can then be used for classification. The structure of these layers depends on the pre-trained network. The simplest type of network is called a series network. Information is passed in order from one layer to the next. But most pre-trained networks are called directed acyclic graph networks, or DAGs. DAG networks have a more complex architecture where information from one layer can be passed to multiple layers. Basically, in Matlab, series networks are just represented as an array of layers. DAG networks, on the other hand, have an array of layers but also need a way to specify the connections between those layers. Series networks don't need this because the connections between layers are implied. To perform transfer learning, you'll need to modify the network to suit your specific problem. But don't worry, most of the network will stay the same. You typically change just the last few layers. For example, here's the end of GooglyNet. Notice that the 142nd layer is a fully connected layer with 1,000 neurons. This takes the extracted features from the previous layers and maps them to the 1,000 output classes. Then the next layer, the softmax layer, turns the raw values for the 1,000 classes into normalized scores, so that, roughly speaking, each value can be interpreted as the network's prediction of the probability that the image belongs to that class. The last layer then takes these probabilities and returns the most likely class as the network's output. When you change these layers, the layer graph has the same feature extraction behavior as the pre-trained network, but it needs to be trained to map these features to your new image classes. When you train with new data, the network will learn that mapping as well as refine the feature extraction to be slightly more specific to your application. You can explore pre-trained networks or create networks from scratch using Deep Network Designer.
On the Apps tab, under Machine Learning and Deep Learning, click the Deep Network Designer icon. For transfer learning, you can choose from the available pre-trained networks. Remember that pre-trained networks need to be installed in the Add-on Explorer before you can use them. Networks that you need to install have a warning icon. GooglyNet is already installed, so let's click GooglyNet to import it. This is a zoomed-out view of the entire architecture. The Properties pane on the right contains a summary of the network. If you're performing transfer learning, the most relevant layers are the input and output layers. You can zoom in and select the input layer to see the image input size. To use this network with your data, you'll have to resize your images to match. Notice that the input size is grayed out. Since we've imported a trained network, some properties can't be edited. Scroll down to see the output layers. Remember, for transfer learning, you need to replace these two layers. Drag and drop the replacements from the layer library. In the fully connected layer, set the output size to the number of classes in your dataset. Then you can delete the original layers and connect your new layers. You should probably check that your new architecture is valid before you try to train it. Click Analyze in the tool strip. There are no errors. Now you're ready to use these layers for transfer learning. You can perform training within Deep Network Designer, or export the network to the workspace.